So the big picture was that we've now got this kind of larger set of things that we're calling Hamiltonian systems. And sometimes these are called Poisson systems as well. But it's any system where you could write the equation of motion in this way, where we write it in terms of how scalar functions f evolve. And if you can write it as there's a Poisson bracket of that scalar function f with the scalar function h, the Hamiltonian for the system, appropriately defined Poisson bracket that satisfies all of those properties, then you've got a Hamiltonian system. So anything that you can write that way. And sometimes we're thinking of n as finite. Later, we'll even talk about n going to infinity, and you can write PDEs in this form. And another subset is everything that we did for several weeks up till now, which are the canonical Hamiltonian systems, where X, we think of the phase space is made up of Q's and P's, and the Poisson matrix, or the kind of non-canonical symplectic matrix, actually is the canonical symplectic matrix. Over here, n is finite, and omega x, think of it as the Poisson matrix, remember? F with G would be gradient F transpose some n by n matrix times gradient of G in general, where this thing, this bracket, this Poisson bracket must satisfy the 5 properties from last time. Of a Lie algebra. Okay, so that's the setting that we're in. When you are in these systems where it's not canonical, so I guess everything outside of this blue region would be the non-canonical Hamiltonian systems. For non-canonical Hamiltonian systems, you get an omega x, a Poisson matrix, which could lead to something called Casimir functions. And that is what I wanted to talk about now. So what are Casimir functions? Well, when you've got non-canonical Hamiltonian equations, and I'll just assume for the time being that any function f that I care about does not have explicit time dependence. So I'm just going to write the equation of motion of f with, it's just f dot equals the Poisson bracket of f with h. When you've got that, then there's a whole new category of, there's a new category of constants of motion. That depend not on the Hamiltonian, which is kind of interesting because like the Hamiltonian is what gives rise to the dynamics, right? But these depend not on the Hamiltonian function h, but on the Poisson bracket itself. That is, Poisson bracket, which means it depends on the Poisson matrix. And often these Casimir functions are called C of x. They're going to be constant. And here's where it comes from. There are, and I guess this is important, they're non-trivial functions. So something that's not just equal to a constant or equal to 0, that would be trivial. There are non-trivial functions that actually have some interesting functional dependence. We'll call those C of x, for which the Poisson bracket of that function with any other function, let's write any other function as f of x. The Poisson bracket of these functions, C, with any other function f is 0. So there are functions C that if you take their Poisson bracket with any other function on the phase space, it equals 0. So we say for all f of x. In particular, if f happened to be the Hamiltonian, well then this is also equal to 0. And that implies that we have a constant of motion. F equals h gives, so this, the Poisson bracket of this, we call these Casimir functions, so that's why the C, but it's just some functions that their Poisson bracket with any other function is 0. In particular, if that function is Hamiltonian, we get 0. So C of x is a constant of motion. Since we'll get that total derivative of C along trajectories equals 0. Okay. So what is the condition for these Casimir functions to exist? There's a few ways to work on it, but probably the best is just to look for the, look at the Poisson matrix and look at its rank. And if it's not full rank, then you've got Casimir functions. So the condition for a Casimir function to exist is that the Poisson matrix is not full rank. So if we write C, the Poisson bracket of a function C with a function f, we'll write this in terms of the gradient of C. So gradient of C transpose omega x gradient of f. If omega is not full rank, then there's the possibility that you could have some non-trivial function C that make this expression equal 0. So let me give the example of the rigid body that we looked at last time. The rigid body, we defined a Poisson bracket using a Poisson matrix. So the rigid body Poisson bracket had our Poisson matrix, which was a function of the phase space, which was the three-dimensional space of angular momentum. The matrix here looked like the matrix version of the cross product. Getting close to the edge. So we had that. Now, you look at this matrix, and then you could ask yourself, is this matrix of full rank? A way to show that a matrix is not of full rank is if you can write one of the columns, let's say column 1, this is column 1, as a linearly dependent on columns 2 and 3. So if we take column 2, I'll just take column 2 here. And I'll multiply it by a scalar, h2, and then I'll add column 3, and I'll multiply that by the scalar h3. Well, what does that give me? Just working this out, I'll get a scalar h1 times column 1. So this matrix, if it had full rank, it would have rank 3. It's a 3 by 3 matrix. This has rank 2. So it's not full rank. So there's the possibility that, well, that's the condition that a Casimir function exists. Okay. What are those Casimir functions? So now we're still talking about the, maybe I'll put a little subscript RB here, so we know we're talking about the rigid body Poisson bracket with, this is our rigid body Poisson matrix. So this, just by the property of Poisson brackets, if you reverse the order, Poisson bracket of f with suite, we get a minus sign. And then this would be minus our gradient f transpose. And we'll write, what does this omega look like? Last time we said, well, this looks like writing h cross product, but in the matrix form. Here's gradient C. So if gradient of C is in the h direction, so it could be anything, any scalar times h, the vector, then h cross product times gradient of C equals 0, because you'd have h cross h, and it wouldn't matter what the function f is. So what do we get there? Well, if you have any function of h bar, which is of the form, and I'll write phi is just some scalar function, any scalar function of the magnitude of h, or let's say the magnitude of h squared, then we would get a gradient of C, which is some scalar that could be a function of h times the vector h. So this tells us the form of the Casimir functions. They're all of this form. Because if we did C with F, oops, rigid body equals negative F with C, rigid body, this equals negative gradient of F transpose A H H cross H, which is 0. So functions of the form any scalar function of the magnitude of the angular velocity of the angular momentum are Casimir functions. Anything. I mean, the one that makes the most sense to us is just the magnitude of the angular momentum, or the magnitude squared. So in particular, if we chose just the magnitude squared, that is a Casimir function. And therefore a constant of motion. Now, does this take away from the physical interpretation that we have a free rigid body? If there's no moments on it, then the magnitude of the angular momentum is constant. No, this doesn't take away from that. It's just another point of view. There are other problems where it's not so, the Casimir functions provide something that's not obvious or couldn't be obtained some other way. In this case, we're just building from something we do know. We have some idea about free rigid bodies. You know, when there's no torque on something in a rigid body, angular momentum's conserved. But here it kind of arises from an interesting mathematical framework. Okay. I will move beyond that now. We're going to go on to something else. Okay. I guess, yeah, just reiterating, the only way you could get a Casimir function is if you've got a non-canonical Hamiltonian. Any canonical Hamiltonian system, I guess that is worth saying. If it is canonical, you won't have a Casimir. If you have a canonical Hamiltonian system, well, then that just means that omega, which should be a function of the phase space, is not. It's just a constant matrix which has that form, and this has full rank. So you don't gain anything by considering the idea of Casimir functions when you have canonical Hamiltonian systems. You need to have a non-canonical Hamiltonian system for these to even show up as a possibility. All right. So I wanted to make a connection with things called Lie derivatives. And these are, it's kind of a generalization of a derivative. So let me talk about that. This is, I guess, the connection of Hamiltonian mechanics. By which I'm thinking this more expanded thing in terms of the Poisson bracket. The connection of Hamiltonian mechanics with Lie derivatives. It's the second time we've come across the name Lie. Lie was a mathematician, Sophist Lie. So there are Lie algebras, Lie derivatives. I think Lie did a lot of things with geometry. Okay, so Lie derivatives, what are they? Let's look at a setting where we've got I'll use the X notation. We've got a phase space, it's Rn. And I'll use some notation for a vector field where I use capital X. So let's just suppose you've got a vector field. This isn't necessarily the vector field that defines your equations of motion. And I might sometimes just write vector field as VF, and I'll write the vector field as capital X at X. So here is like a little sketch of a vector field on a grid, the way we're usually thinking of it. So at the point X, little x, we've got big X, is the vector at that point, and it has components. Let's say we've got big X sub 1, big X sub 2. So this is a 2D example. At some other point, we might have a slightly different vector and so on, right? We've got a smooth vector field. So we can write the vector field X, capital X, in terms of its individual components. And we're thinking in terms of the n-dimensional setting. So there's x1, x2, all the way up to xn. Those are the components. And we're familiar with things like this in mechanics, like from fluids. If you look at the fluid vector field in 3D, you've got the 3 components, and you often write them as U, scalar V, and W, the UV and W components of a fluid. But now we're just thinking n-dimensional. So suppose you've got a vector field, X, and suppose you also have a scalar field, F of X. Then we can talk about the derivative of F along the vector field X, or we call it the Lie derivative. The Lie derivative of F along the vector field X is, and this is where you get to write the fancy L. This is how it gets written. The Lie derivative, kind of with respect to the X vector field of F. And all this is the directional derivative of F along X, which should be familiar from calculus. So this is the directional derivative of F along X, which we are used to writing as gradient of F, usual dot product, vector field X. So this would be the directional derivative for any vector field X, capital X. We're not necessarily thinking of vector field X as the equations of motion, but suppose it does give the equations of motion. So if the equation of motion for our system x dot equals, and it is this vector capital X, then the total derivative of F equals, right, it's df dt, the total derivative of F along trajectories. We would write this in terms of chain rule. So this would be a sum of the elements 1 through n, partial F, partial xi, and then the derivative of xi with respect to time. So this is just going to be, this is just writing out in component form, gradient of F dotted with x dot, usual dot product, or gradient of F dotted with x, which we set up above, is the Lie derivative. So F dot equals the Lie derivative of F with respect to the vector field X. So you might say, okay, you've just shown me some new fancy way to write things. Things get interesting if capital X, the vector field, is Hamiltonian. So what if X is a Hamiltonian vector field. Just meaning X arises from a Hamiltonian function. Or we could say F is generated from a Hamiltonian function, H, so that we would write X as like X sub H. Just to remind ourselves, this comes from a Hamiltonian function. I don't know. What if? I'm gonna put a question mark. What if? Well, then we know something about the form of the vector field. It's not just any old vector field that I can imagine. It has some constraints on it. If I have a Hamiltonian vector field, that means that X dot equals X sub H. And from what we did up above, or actually last time, the vector field can be written as, in terms of the Poisson matrix, omega, and the gradient of H. So this is a special form of a vector field. You can't put all vector fields into this form, only certain types, Hamiltonian ones. Okay, so then getting back to F dot, this would be the Lie derivative of F along the vector field X of H. And so that's, what's another way to write that? Gradient F dotted with X dot. Okay, gradient of F, we know how to write X dot. Omega X, sorry, yeah, the Poisson matrix times the gradient of H. Or another way to write this is just gradient of F transpose omega gradient of H. Then we go, oh, well, I recognize that. This is how we wrote the Poisson bracket. So that means the Lie derivative of F with respect to a Hamiltonian vector field that's generated by the Hamiltonian function H is the Poisson bracket of F with H. So there's a connection between the Lie derivative and the Poisson bracket. The Lie derivative of a scalar field and a Poisson bracket. And the Poisson bracket when that vector field is Hamiltonian. I guess the vector field of interest. Okay. And yeah, that just is, okay. You might think, okay, nothing's been gained yet. The neat thing about Lie derivatives is they're not just directional derivatives of a scalar field, which is the thing that we learned from calculus. You can take the Lie derivative of a vector field with respect to a vector field. And then things will start getting more interesting. So you can take the Lie derivative of another vector field. So how will I write another vector field? I'll use capital Y with respect to our original vector field X. So fancy L, Lie derivative of the vector field Y with respect to the vector field X. I guess you could call this a directional derivative of Y with respect to X. There is an example from fluid mechanics that I might mention as an aside. Let me put my little brackets here. This isn't coming out of the clear blue. There is some motivation from fluid mechanics, which is sometimes called the fluid derivative. And this is where people use different kinds of notation. So when does this get used? Like the fluid derivative of the vorticity along the fluid velocity. And where we're thinking of 3D, so the vorticity vector field along the fluid velocity should be vector field V. What is the vorticity? The vorticity is the curl of the velocity. But you could write the Lie derivative of the vorticity with respect to the fluid velocity. And some books will write this type of thing as a capital D omega. It's like the time derivative of the vector omega along the Lagrangian path of the fluid element. And then this is written in this kind of cumbersome way, V dot grad omega minus omega dot grad V. I think of it as you've got your vorticity at a point and you've got the velocity. And this thing will evolve. Here's like a fluid parcel moving to a new location. The velocity over here has to be tangent to our path. And how does the vorticity change along there? Well, you would calculate what in most books is written that way, but it's a Lie derivative. It's the directional derivative of one vector field with respect to another vector field. This has the interpretation of the rate of change of the vorticity vector. Along fluid paths. Usually only in a like fluids course would you try to wrap your head around that. And hey, now let's try to wrap our head around just a generalization of this to n dimensions. Yay, for arbitrary vector fields. Okay, well, the directional derivative of one vector field with respect to another is actually a new vector field. So the directional derivative of some vector field with respect to another vector field, and these are equal dimensional, they're full dimensional and dimensional. This is another vector field, which I guess I'll use capital Z for that. Z is another vector field. And we could write it component-wise. So, right, Z is this vector field. got components, Z1, all the way to Zn, just like X does and just like Y does, the vector fields. The Zi component can be written in terms of the components of the X vector field and the Y vector field. This way, J, sum of J from 1 to N of Jth component of the X vector field, and then a partial derivative of Y. What? This is Y sub I partial X J minus Y J partial X I partial little x J. Another notation, sometimes people don't write this kind of capital L stuff. They'll write this a different way. They'll write Z is square bracket X with Y. This is called the Lie, there it is again, Lie bracket of X with Y. So that this component here, this Zi component is it's the ith component of this Lie bracket. The Lie bracket, it's showing up here. It also shows up in control theory, which I guess is kind of an aside, because I'm not going to say much about it. The way it shows up in control theory is if you have two kind of infinitesimal controls that you could do. The X corresponds to one control, Y corresponds to another. You want to know, if I combine these two controls, can I get motion in another direction? And so if Z ends up being in another direction, then yes, you can do that. So it becomes a fancy way to find out if you can, using two controls. Like for a car, I can go forward and backward instantaneously, and I can steer. So how does parallel parking even theoretically possible? You know, I can't instantaneously move sideways, but by combining going forward and backward and turning, I am able to go sideways. And calculating the Lie bracket of forward, backward, and steering vector fields would show that. Okay. It's the Lie bracket, so Z, the Lie bracket of X with Y. This is also sometimes called the commutator. Of the vector fields X and Y. You've probably heard commutator language in context of matrices. You know that if two matrices commute, then two square matrices A and B, if they commute, then if you do A times B, that's the same as B times A. Here, in terms of vector fields, it's different. If X, was there a question?
Yes. Does this relate to quantum mechanics stuff like momentum and position commutation relations?
I don't know off the top of my head. I mean, for the matrix stuff, yes, because they usually write in quantum mechanics. You can write what, like measurements in terms of matrices, and so if an observable corresponding to something, you write it as a matrix. Yeah, so there, in terms of the matrix commutation, yes. For this vector field stuff, I think no.
Oh, okay.
Yeah.
Because in quantum mechanics, if two things commute, then there's uncertainty. So I was wondering if that's the same here.
I don't know. I'll say I don't know. Yeah. Good question though. Here, if x and y, the two vector fields commute, that just means that if you do this calculation of the Lie bracket, or essentially the Lie derivative of y along x, you get 0. And x and y, the vector fields, are said to be compatible. And what does that mean, compatible? We'll have to, I'll get to that. All right, so I was talking about these derivatives of things, like directional derivative of a vector field along another vector field. And then I brought up this notation that, oh, you could, it's the Lie bracket. And the Lie bracket is also a Lie algebra. And so what does that mean? It has all those properties as the properties that we talked about last time. 1 through 5 from last time. So the Lie bracket of any vector field with itself is going to be 0. The Lie bracket of x with y equals negative. Lie bracket y with x, and so on. Also the Jacobi identity. And there's no, I think there's no simple example that we're used to, kind of like the cross product was, but I don't know, maybe cross product is it. We could do a geometric interpretation of the Lie bracket, and that's kind of fun to do.
A quick question about the relationship between the Lie bracket and the Poisson bracket.
Okay.
So does the fact that the Lie bracket is defined on vector fields kind of end up implying that the Poisson bracket can be defined between vector functions and scalar functions? Or do you have to go component-wise for the Poisson bracket?
So the Poisson bracket is defined on scalar functions. There will be a connection between the Lie bracket and Poisson bracket, but it's only true for Hamiltonian systems. This thing that this Lie bracket you could do for any vector fields. Okay. But the relationship will, I'll probably just give that next to illustrate it. But does that answer?
Maybe. I guess I was just wondering if you can make the claim. So Poisson brackets are only considered defined on scalar fields, not vector fields, right?
Correct.
Or scalar functions. Okay.
Yes. The space of scalar fields. All right. It's an operation on the space of scalar fields.
Okay. Yeah, that was just my question.
Okay. Whereas, yeah, the Lie bracket is an operation defined on the space of vector fields. But let me give a geometric interpretation that has helped me. So, how to do this? We've got a point. We're starting at our point x, and at x, here's big X, the vector field at x. I'm trying to give a geometric interpretation of what z is. So maybe I'll write that in green. C, Lie bracket of X with Y. So you first follow or maybe I'll say go forward. Go forward under the vector field capital X for a small time step dt. Not maybe infinitesimally small, but small. So go forward under X for time step dt. So if I'm starting here, there's my vector field. I'm along this long enough that maybe there's some curving. And now I'm here at this new point. And at this new point, I follow the vector field Y. So now go forward under the vector field Y for time step dt. And that will take me, this will curve a little bit too, and that takes me here. At this point, the X vector field is going to be different because I'm at a new point. And I'll just draw it like this. Now I go backward under X. So I'll draw that dashed. Go backward under the vector field X for time step dt. If you want, that means I follow the negative X vector field. And this will take me, I don't know, somewhere. And then at that point, Y is slightly different too. Here's Y. And I'll go backward under Y. So that takes me somewhere. It doesn't actually take me back to the original point. It takes me somewhere. There's a little bit of displacement. This displacement is proportional to the vector field Z times this time step squared, where Z is the Lie bracket of X with Y. So if two vector fields are compatible, meaning the Lie bracket between the two is 0, that means I would be back to where I started. So if X and Y commute, this procedure would take me back to where I started. But in general, it won't, because two random vector fields probably are not going to commute. Okay. Yeah, so what I set up above about Lie brackets, that was true for any vector fields. Now I'm going to specialize the Hamiltonian vector fields. So let's say I've got a Hamiltonian vector field, and this might look weird, but I've got X is the Hamiltonian vector field generated by the scalar function f. And X sub G is the Hamiltonian vector field generated by G. Might say, what does that even mean? Like, what's the actual Hamiltonian? Well, that's part of the punchline. Maybe there is no actual Hamiltonian. Well, here's the neat thing. This might have a name, but I don't know. The Lie bracket of X sub F, the Lie bracket of X sub G, is equal to a vector field generated by the Hamiltonian function Poisson bracket F with G. So that is the connection between Poisson brackets and Lie brackets. And it's nice. So if the Poisson bracket of F with G equals 0, well, the Hamiltonian vector field generated by 0 is just 0. 0 is 0. So the vector fields X sub F and X sub G commute. They're compatible. What's another way of saying this? They correspond to compatible constants of motion. And that will take some explaining. What it means is that F equals a constant describes a codimension 1 surface in the phase space. That can coexist with G equals constant codimension 1 surfaces. Okay, and I will give a geometric example of that. Okay, yeah, all right. I'm going to use notation like this, gradient F. I might write it as grad F. What is this? These are vector fields. This is a vector field normal to level sets of F. You know, F equals a constant is a level set. Level set of F. So grad F, if I had F equals constant as a surface, then grad F is going to be normal to that. Let's look at some canonical Hamiltonian illustrations of this geometry. So like 1 degree of freedom. In 1 degree of freedom, let's say, all right, I've got a Hamiltonian system with H, Q, and P equals our favorite thing in the world, the harmonic oscillator. It's just a rescaled harmonic oscillator. In the X notation, we've got the X vector is just Q and then P. The vector field that's the equation of motion would be x sub h. And we know what the components are. It would be, right, the Poisson bracket here is just equal to j, which is 0, 1, -1, 0. So this equals omega grad h, which is just p negative q. Okay. Let me sketch the phase space. Here's q, here's p. Level sets of h. We know level sets of h are important because in 1 degree of freedom that corresponds to what trajectories do. So let me sketch some level sets. Here's a level set. Here's another level set. Level sets of h are in red. The gradient of h would be, I'll just write grad h. This is a vector field, normal to the level sets of h. So I'm writing this in blue, right? It's just radially outward. It's the level set. Sorry, the gradient vector field. What about, right, this is J. What is J gradient H? I'm going to give this a name. Instead of it being the gradient, I'm going to call it S grad H for skew gradient. This is the Hamiltonian vector field. To the direction trajectories go, and it's going to be along level sets of H. So we know what, this is this simple harmonic oscillator. So it's for each arrow, like this one in the upper right, well, you kind of rotate 90 degrees and you get this black arrow. It's along the level set. And here we chose a Hamiltonian function that has some physical relevance. Anything that's got, that shows this harmonic oscillator type behavior, it's going to be topologically equivalent to this. But for any scalar function f, we can define a Hamiltonian vector field for f, even if it doesn't correspond to total energy or anything. So does that mean anything? Maybe. I'll put this in orange. For any scalar function, f, we can define a Hamiltonian vector field generated by f, and at least given this notation up above, it's just going to be the skew gradient of f. So we could write it this way, x sub f. And we're thinking in terms of canonical Hamiltonian systems now. So I could use, right, j gradient of f. This is just s grad f. It's first you take the gradient vector field of f, and then you multiply it by j, which will do something. It rotates by 90 degrees if we're thinking of a 1 degree of freedom system. In 2 degree of freedom system, now we're talking about 4-dimensional phase space, so I don't know how it's rotating it. So for f equals to some Hamiltonian that has physical meaning, h, this vector field is special because it relates to motion. So j grad f, I guess what we wrote is x sub h, j grad f. The skew gradient of h has the special property that it corresponds to how trajectories evolve if we've chosen the right h. Okay, let's try to interpret this grad stuff and s grad stuff in a 2 degree of freedom example. Okay, so 2 degree of freedom is where things might be harder for us to interpret. We've got a 4D phase space. Q1, Q2, P1, P2. The Hamiltonian will be some function. All that I really care about now is it's taking in where you are in the 4D phase space and spitting out a real number. And let's, so h is the function, let's say we're choosing some constant e. E is just some scalar, okay. H inverse of e, this is just, this just means, it's another way of writing the 3D level set of h, which we previously called an energy surface. So this would be the energy surface with energy E or energy manifold. We know that h is a constant of motion, but there could be others. So the Hamiltonian function is a constant of motion. But there could be others. Let's assume there are 2 constants of motion. One of them might be h, I don't know. But just for sake of argument and for some geometric interpretation to end on, let's assume there are 2 constants of motion. So by constants of motion, I mean functions which remain constant along trajectories. So f, I'll write one of them as f. So it's a function of the phase space, Q1, Q2, 1, P2. Constants of f, right? These are, it would be 3D level sets. There's going to be 3D level sets. And let's say there's some other function g. G equals to a constant, also defines 3D level sets. Now, how can you have motion along two 3D level sets in a 4D space? Well, we can try to build up intuition by looking at lower dimensional things. If our phase space was 2D and we had two constants of motion, all right, one of them, a level set would be just a 1D curve, and the level set for another one would be just another 1D curve. And unless they happen to be parallel, they would intersect in just a zero-dimensional set. A 0D set is the intersection, which means you wouldn't have any motion because you just have to be at that one point. In 3D, let me try to sketch 3D. 3D is kind of hard. There's our little 3D phase space. Yeah, it's really hard. Okay, so here, in 3D, you'd have 2D level sets. So you'd have surfaces, which it's hard to draw. Okay, so here's a level set for one thing, and then generically there'd be like some other level set, and these would intersect in what would be a 1D set. So if you had two constants of motion in a 3D phase space, things would have to generically be along 1D sets, which, hey, that's what happens with the rigid body equations we talked about last time. So what about in 4D? In 4D, two 3D surfaces generically intersect. We're just kind of doing dimension counting. So by this trend, 0D, 1D, they should generically intersect in a 2D set. Okay. So 2D surface. All right, we have to define what the gradient is. Gradient of anything will be, it's like you operate, you take certain partial derivatives. You take partial Q1, partial Q2, partial P1, partial P2. And you just operate on a scalar function. We could also define the skew gradient or S grad, and it's just going to be J times the gradient, which means in this first slot, it's partial P1, partial P2, and then minus partial Q1, minus partial Q2. Yeah, like we talked about above, the gradient, at least in the 1D example, the gradient gives the vector field that's orthogonal, normal to level sets. Of the scalar function that you take the gradient of. What about the skew gradient? Skew gradient is different. Skew gradient, it's one vector field that is tangent to the level set. There would be two others. This is just one. Two other vector fields, two other independent ones. So along S grad F, so we've, by assumption, there are two constants of motion. How is that possible? Along S grad F, that vector field, we want G to remain constant. And the condition for this is what? Would be, if we want G to remain constant, then we take grad G, that vector field, and dot it with S grad F. And we want that to be 0. So we want those two vector fields to be orthogonal to each other. But what's another writing this? Well, grad G is just grad G. This is a dot product, so grad G transpose times J grad F. Sorry, J, let me do the nabla notation. J nabla F equals 0. So it's just, we're just rewriting it. This is the same as saying the Poisson bracket of G with F equals 0. What is the punchline? So F and G are compatible, that phrase I used up above, are compatible constants of motion if the Poisson bracket of the two vanishes. Another way it is said is that F and G are in involution. And I will give you more that you can read about this, but this does get to, I think, at least in homework problem 1. I was reminded of this during office hours. Part B, you're asked to calculate the Poisson bracket of a few things. And one of the questions is, are the functions fi compatible constants of motion? And so to figure that out, you have to take the Poisson bracket of all of them with each other and see if they are. This is really quick, but just, this is another interpretation of the Poisson bracket of two scalar functions equaling 0. If I've got level sets of G, they would be preserved under the vector field generated by X F, or generated by the Hamiltonian vector field of F. But it's also true that the opposite, right? Because I could have level sets of F. And they're preserved under the vector field generated by G. The Hamiltonian vector field. So that brings up things like, what's the real Hamiltonian vector field? And, well, we'll get to that next time, I guess.